Hello, everyone. My name is Oksana Golovko. I am the Associate Professor in Environmental Chemistry from Swedish University of Agriculture Science, SLU, Uppsala, Sweden. And today I would like to give a presentation about food waste and organic micropollutants. This presentation is aimed for broader audience, and if you would like to get more details about the topic, by the end of this presentation, you can find a link to scientific publication which can be read. So let's talk about the food waste. In the push to save our planet, few ideas as exciting as challenging as the circular economy. The concept is very simple. Instead of extracting resources, using them, and tossing them away, we keep them cycling through the system. This way, nothing is truly waste. It's just a resource waiting for a new life. One of the examples of this approach is how we handle food waste. We would like to have responsible consumption and production in all sectors. And there is a need for sustainable solutions, which include source separation, resources, recovery, and overall waste production. And every year, millions of tons of food end up in landfill, rotting away and releasing harmful greenhouse gases. In Sweden and many other countries, food waste is no longer simply thrown away. Instead, it's increasingly sent to biogas plant where it undergoes a process called anaerobic digestion. This figure is an example how it happens. So when we do collect food waste from household, restaurants, and other places, we transfer it to we transfer it to biogas plant where it undergoes different processes by producing biogas, which can be used for heating, producing electricity, etc. And the other products can be generated, which is digestate or fertilizer, which can be used by farmers on farmland or urban hydroponic. But let's have a look on the anaerobic digestion process. So microbes break down the food scraps in airtight tanks, producing biogas and nutrient-rich sludge known as a digestate. And farmers already use it to fertilize feed, cutting down on chemical fertilizer and helping close the nutrient loop. During this process, uh, the reduction of the total mass of the easily degradable fraction of starting material is happening. And this digestate or fertilizer is rich of different nutrients. And as cities grow and green space shrinks, more people are turning to urban farming, including hydroponics, where you can grow plants directly in water-based nutrient solution, no soil is needed. And digestate from food waste could be an ideal nutrient source for these urban farms, providing a local circular solution that transforms food waste into the food product. But before we start pouring digestate into the urban hydroponic system, there is a question: what else do we have in that sludge? So while anaerobic digestion reduces the bulk of food waste, it doesn't eliminate everything. Heavy metals, some of organic micropollutants such as pesticides, residues from pharmaceuticals, they can be found in food waste. And also some pathogenic bacteria might present both in environment might cause environmental and human health risks. And in some cases, these substances might even become more concentrated during the treatment process. But before going into details about digestate, I would like to turn your attention into organic micropollutants. So what are these chemicals? These chemicals include big group of different contaminants, of different compounds, such as pharmaceuticals, medicine, industrial chemicals, food additives, personal care products, stimulants, etc. We use these chemicals in our daily life for producing something to improve our health life, to make food, to protect plants from insecticides and different pathogens, and we are heavily using them in industry. This figure shows that every year the consumption and production of pharmaceuticals and pesticides, which belong to organic micropollutants, keep increasing. We keep producing and consuming new products every time because we would like to improve our lifestyle, we would like to improve our life conditions. By doing that, we also contribute into releasing of these organic micropollutants into the environment. There are so many sources where you can find organic micropollutants. One of the main sources is domestic waste, where, for example, pharmaceuticals, some food additives, sweeteners can be disposed inappropriately and mixed with food waste. Hospitals also the main source of pharmaceuticals and the other components which can be used for treatment of different diseases. And of course, industries where we can find different group of organic micropollutants contribute to the release of these compounds into the environment. And once organic micropollutants reach the environment, they can affect different fields at different levels. When we are talking about aquatic environment, organic micropollutants can target aquatic organisms such as fish, aquatic plants, macroinvertebrates, and they can affect their life drastically. If organic micropollutants can end up in soil or manure, they can be uptaken by plants which we consume by the end of the day, and indirectly these compounds can affect our health. When we are talking about food waste and organic micropollutants, it's this part where attention has to be paid. When these compounds are mixed with food waste, by the end of the day, after the anaerobic digestion, the fertilizer might contain some of these contaminants, and if they are still present in the final digestate, they can end up in the plants. And especially if digestate contain these hidden chemicals, is used as a fertilizer, these contaminants could end up back in the plants, and that's why it is very important to investigate what kind of organic micropollutants we have there, because there is a concern for urban farming system where plants grow directly in nutrient solution. And increasing the knowledge on the characteristic of anaerobic digestate is very important. And in our study, we tried to analyze different organic micropollutants in the food waste to check what kind of heavy metals we might find there, and we analyzed foodborne pathogens. But let's have a look what exactly have been done. So we visited 3 biogas plants in Sweden, and you can see them in this table. They are labeled BPA, B, and C. all of which transform organic waste into energy and fertilizer through anaerobic digestion. These facilities use slightly different recipes, a mix of food scraps, manure, slaughterhouse waste, and industrial waste, as you can see from the table. And at each plant, we collected about 2 liters of the final product, the biofertilizer. And we took special care to keep everything clean using pre-washed bottles. And we freezed our samples back at the lab to preserve them until analysis. We also collected additional samples for microbiological tests from 2 different points in the process, after the first hygienization step and from the final fertilizer product. And we checked for 5 common foodborne pathogens and 3 types of antibiotic resistance bacteria. We also checked for heavy metal content. We performed chemical analysis and risk assessment. For the chemical analysis, we screened for 133 different chemicals or organic contaminants, a big family that includes 60 different pharmaceuticals, 58 pesticides, smaller group of industrial chemicals, parabens, stimulants, vitamins, and sweeteners. Chemical analysis was performed by using ultra-high performance liquid chromatography tandem mass spectrometry. And it was very important to analyze them because these substances can enter the waste stream through the leftover food, household products, and industrial residues. And we also estimated how risky it might be to spread the fertilizer on the field. We used models to calculate the risk quotient, RQ, for each chemical, which indicates the potential threat to soil organisms. And when RQ above 1, it suggests a potential risk, while values below 1 are generally considered safe. So, what did we find in our results? When it comes to microbial characterization of the anaerobic state, in accordance with the certification requirement from Sweden, all investigated organisms showed similar occurrence and low levels at the 3 studied plants. And it's good news. We didn't find any microbial pathogens in our samples. When it comes to heavy metal content, we analyzed heavy metals like cadmium, lead, and mercury. As you can see from this table, the concentration of heavy metals were lower than maximum accepted levels according to the certification. And our results suggest that biofertilizer producers, they are doing really good job controlling metal contamination. And also it helps by clear rules and regular monitoring. But when it comes to the chemical analysis, we found some interesting results. As it was mentioned before, we checked for 133 different compounds, from pharmaceuticals to food additives, and found 48 of them, at least in one sample. Among positive compounds, we found stimulants such as caffeine and nicotine, and also theobromine, the compound found in chocolate and tea. And no surprise there because we were analyzing food waste. Also, we did find some pesticides, paraben, and sweeteners. Also, 2 vitamins were found in our samples. And when it comes to hydroponic, we would like to know that when biofertilizer is spread on the field uh, as a source of nutrients, so will it contain any of these chemicals after dilution? And like what will happen to these chemicals in the biofertilizer? So we calculated how these chemicals would dissolve if about 2.4 grams of biofertilizer were added per liter of water. It's a typical setup for hydroponics. And what we found that stimulants, again, caffeine and nicotine, stood out with the highest dissolved concentration, and some water-soluble chemicals can accumulate in leafy greens and other vegetables grown in hydroponics. So there is a concern for future research, like could these hidden chemicals end up back on our dinner plates if we are using this biofertilizer in hydroponics or on agriculture fields? That's why we did calculate environmental risk. And long story short, green light for now. So when we estimated the overall environmental risk of these fertilizers, we used the risk quotient, where we compared predicted soil concentration to levels considered safe for soil organisms. And again, good news, even the most abundant chemicals like theobromine was far below risk thresholds. And these results, similar to previous studies where it was suggested that most of organic contaminants pose minimal environmental risk at current concentration. But it's important to remember when we are talking about organic contaminants, these chemicals, they don't always act alone. So their combined effect, also called mixture toxicity, can be more complex and still need to be studied in the future. To have a look at the bigger picture, as a conclusion, we can say good news. All investigated microorganisms showed similar occurrence and very low levels at 3 studied plants. Also, concentrations of heavy metals were lower than minimum acceptable levels according to certification. Despite the fact that we did find different kind of organic micropollutants in the Digi state, so far there is no risk, which is good. And it brings us to bigger picture that looking forward, there is a need for long-term studies to understand how these chemicals profile might change over time and across different locations. And this knowledge could help different authorities to develop a priority list of these compounds, and it can eventually lead to new certification standards for organic micropollutants in the biofertilizer. And as more cities and farms embracing biofertilizer to close the loop and reduce the waste, knowing what exactly is inside is very important, not just to protect the environment, but also to keep our food safe. If you would like to know more about organic micropollutants, heavy metals, pathogens in digestate based on food waste, please read this article where you will find more details. Thank you very much for your attention and have a great day.